All right. That's a cue that means that we're going to start. Yeah, thanks all for coming again. So today we have Gabriele Cesa here to talk about a bit about harmonic theory or like representation theory and for steerable group convolution. So last Tuesday I already gave an introduction to this, but since this is quite kind of advanced topic in equivalent deep learning, or because of the mathematics, I think it's great that today we have a second iteration on this. Yeah, by Gabriele over with some actual code examples. So you see there will be theory mixed with code. And just want to say again, like I mentioned some libraries for coding up equivalent architectures. He's the main author of this ESCNN library for steerable convolutions in 2D and 3D. So yeah, I cannot imagine any more expert on this topic than you. So it's great to have you here. And yeah, you can go ahead.
Thanks, Eric. Well, thanks for having me here today. And well, first of all, I think you have access to this website, right? So you should be able, if you have a laptop, to open the tutorial. Maybe that's nice to follow. You don't have to code anything up today. There's like all the solutions. You can find 2 versions of the tutorial, one without solutions that you can try at home. But I thought that maybe for today we just try to go through all of it together, right? And you can take this more as a recap of what you've already seen with Eric in the lectures, and together with some code to try to play with these mathematical tools and these concepts. That's it. We are going to use for the first part. Well, actually, for the whole tutorial, my library, because it implements a bunch of mathematical concepts we need. That makes it a bit easier to work with. Hopefully, it makes it also a bit more fun because we can play with these objects, try to combine them and see what happens, rather than just reading equations on the books. Can you see well the screen? I can zoom a bit more, maybe. Fits. But yeah, okay, so let's start. I assume that you already are a bit familiar with the concept of a group convolution. You should have seen this in the previous lectures and tutorials. So the idea of, take a filter, right? We transform it with every possible group element, and we generate a feature map over the new group, right? It's as a basic building block. And basically the idea behind Steerable CNNs is generalizing these concepts a bit further. One reason why we need that is because the basic definition of group convolution can be applied only when you have when you can kind of manually iterate over all the group elements, right, and store a value for each of them, which kind of works only when you have a finite dimensional group, right? While Steerable CNNs provide us a framework to generalize this further to continuous groups by using essentially the theory of harmonic analysis over compact groups. If you're a bit familiar with Fourier transforms or normal harmonic analysis, you can imagine this is a kind of a generalization of the standard Fourier transform rather than over temporal signals, so like one-dimensional spaces, but over groups which are just more general spaces. And this allows us to model essentially features over our bigger groups, but with using only certain frequencies. So it's just a different way to discretize these features. If you're not familiar with that, it's going to become a bit clearer in the next 2 hours. I just wanted to give you a preview of that. Okay, some prerequisite knowledge is group theory, and some linear algebra, essentially. The rest we're going to see that together. If you're running this tutorial in parallel, you can see again a link here for the tutorial on Google Colab. Here is how you install basically all the dependencies. This in particular is our library. These are a few dependencies we need to be able to run it. So yeah, let's go on. I think that this part is similar to the previous tutorial. So this is standard stuff to just set up the environment. Of course, we don't have time to train the models now. So these models are cached somewhere on the cloud, and we are just going to download the pre-trained models. But you should be able to remove these checkpoints and train these models yourself on Google Colab. So we skip over this first part. and we go to the more interesting one. Okay, so let's start with the representation theory and harmonic analysis. Here you find a link for the library with some also documentation in case you want to check it. First of all, we have to install the library. That should be taken care of by Google Colab, and then we go on the more theoretical part. So you are familiar with the groups, right? Imagine like a group as basically a set of transformations which we can combine, and when we combine them, we get new transformations inside the group. A simple example we are going to use in this tutorial is the group of 8 rotations. So rotations by multiples of 2 pi over 8. This is called the cyclic group of order 8. We just identified with this C underscore 8. That's useful to model, for example, rotation equivariance to multiples of this angle, right? So in total to 8 rotations. In the library, right, groups are actually subclasses, right, of the generic abstract class group. Kind of makes sense. And we can instantiate like a cyclic group of order n, so with n rotations, simply by just calling this factory method. We can check that this group indeed has order 8, so it has 8 elements by just calling group.order. That should be quite intuitive. Groups have identities, right? So it's the transformation that essentially does nothing. Often it's identified by the letter E, like in mathematical textbooks. We can access this element with g.identity. In the library, there's such a thing as a group element, is a class itself, right? So which implements a bunch of useful properties. So for example, we can sample random elements. This is, for example, a rotation by 2 pi over 8. But we can also combine group elements as you would normally do. So we can multiply group elements to find a new group element. We can take an inverse of a group element to obtain a new group element. So for example, if we generate 2 random rotations, one by 6 times 2 pi over 8 and one by just 2 pi over 8, we can combine them, right, to get a rotation by 7 times 2 pi over 8, or take the inverse. So for example, the inverse of 6 is 2. You can verify that if you rotate by 6 times this rotation and then 2 times this basic rotation, you get again the identity. So you go back to the starting point. So yeah, that's pretty much what we need to know for groups. Just a brief recap of what a group is. And the rest is going to be about group representations. Group representations are, as we are going to see, what allows us to build this Fourier theory, this harmonic analysis for compact groups. But let's start from the basic definition of a representation. You can find, again, a summary of the definition you have already probably seen, but let's see that again. So for a certain group G, right, a linear group representation is essentially a map that associates to each group element a D by D matrix. So essentially a linear operation on the D-dimensional vector space RD, right? And this map needs to satisfy a few properties. So first of all, these matrices need to be invertible. This is sometimes referred to the linear group, general linear group on RD. But just imagine these are D by D invertible matrices. And second, this map needs to satisfy this property, which basically tells us that the multiplication of group elements is compatible with the multiplication of the matrices. So if we associate a matrix to the group G, the group element G1, and a matrix to the group element G2, I'm missing a, sorry for the typo here. This should be the same matrix, and we multiply them. This should be the same matrix which we associate to G1 times G2. Right? This is what is usually called a group homomorphism. It's a bit of a technical term. Yeah. You can just forget about it and just imagine that this is telling us that the multiplication of matrices is compatible with the multiplication of the group. Let's see a couple of examples of representations just to make it a bit more concrete. The first simplest type of representation is the trivial representation that basically give us, can you see my pointer, right? Yeah. That basically gives the value 1 to each group element. And you can imagine the number 1 as being just a very simple 1 by 1 matrix, right? Acting on the vector space of dimension 1, right? And well, because everything is mapped to 1, this property is trivially, satisfied, because 1 times 1 always gives you 1, right? And we can instantiate this representation by just taking the group and then calling the attribute trivial representation. This representation is an instance of the abstract class representation, right? Which implements a few useful properties we will use later to combine representations. But let's start by playing a bit with this object. A representation is a callable function, so we can now basically sample 2 random group elements, right? And then we use a row as a function, right? So we pass row one of the group elements, and this would generate a NumPy array, which represents our representation, which in this case, of course, is just a 1-by-1 matrix with value 1. So we can also just easily verify that the representation of G1 times the representation of G2 is equal to the representation of G1 times G2. That's, I know, very trivial. Just this is the simplest example we can look at. And of course, the trivial representation of size 1. This is the dimension D we saw before. Let's look at a bit more complex representation. Now we look at the group of 2D rotations. What we saw before was the group of 8 rotations in 2D. That's like a discrete group of size 8. We can look at another group now, which is the group of all continuous rotations over in the plane, right? It turns out that the 8 rotations is, of course, a subset or subgroup of that. But this is has its own name, and it's called the SO2 group. So it's the group of the special orthogonal group in dimension 2, which is the group of all essentially 2D orthogonal transformations which have determinant 1. And you can trust me that this is equal to all the matrices in this specific form, right? Where you have some angle theta between 0 and 2 pi, and then you have cosine, minus sine, sine, and cosine. This represents literally a rotation of a 2D vector around the origin. And the nice part is that this specific 2x2 matrix, which we use to define the SO2 group, is actually itself a representation of the SO2 group, right? Imagine we abstract a bit away, right? And we think about elements of the group as angles between 0 and 2 pi, right? And this map that associates to the angle theta, right? This 2x2 matrix is a representation of the group. So a rotation by construction, right? A rotation by theta times a rotation by alpha, right? Gives you, generates 2 matrices of this kind, which when we combine actually give us a rotation by theta plus alpha. That's the general idea, but we can verify this in practice. We call this a standard representation of the SO2 group, just to basically say that this is how the SO2 group is itself defined. And we can now verify that if we take 2 random rotations in SO2, so for example, a rotation by 4.8 radians and 4.7 radians, right? We can combine them, right, to generate a rotation by 3.27 radians, right? But now we can also generate the corresponding representations as rotation matrices, which of course we can combine, and we verify that the 2 operations give us the same result. Is this making sense for everyone so far? Feel free to interrupt me while during the tutorial for any questions or doubts. Just want to make sure that this basic construction is clear, because we are going to build on top of this now some more complex stuff. Okay, cool. So yeah, the tutorial includes a bunch of questions here and there. I'm already giving you the answer. There's some demonstration. I don't think I'm going to go through the proofs, because I think that's a nice exercise to do on your own. And also it takes some time to go through all the proofs, but you can think about those yourself. One thing that is useful here to know, though, is this kind of properties. You can trust me that these are true, right? And then you can try at home to verify that. But basically, by the definition of a representation, it must be the case that the representation of the identity element is the identity matrix. You try to think about that, but this kind of makes sense, right? And that the representation of a group element, the representation of the inverse of a group element is equal to the inverse of the representation. So essentially this representation map, right, commutes also with the inversion of the group elements. So yeah, you can verify this yourself at home. Okay, now we introduce another tool that we can use to build more complex representations. Because so far we looked at two very simple representations that are not maybe super interesting, but we can build more complex and larger representations by combining two smaller representations. This operation is called direct sum. So given a representation row 1 of dimension d1 and a representation row 2 of dimension d2, we can now build a bigger representation of dimension d1 plus d2 by just stacking them on top of each other. Actually, we stack the matrices in this kind of block diagonal structure, but you can see that the vectors, right, the vector spaces these two matrices act on are just obtained by stacking the vectors in a bigger vector, like you would do in NumPy with NumPy.concatenate. I don't know. So yeah, this is a D1 dimensional, this is D2 dimensional. The output, right, you can kind of see this is D1 plus D2 dimensional. We can do this by just using a plus operation over the representation objects, right? So this generates a new representation which evaluates to this direct sum. So for example, we can take the standard representation we saw before, right? We take the direct sum with itself that generates kind of two copies of it. And we see that when you evaluate it on a random group element, it just basically pastes twice the same representation here. Yeah, makes sense? Cool. And of course, we can do this more than once, right? So we can build arbitrarily larger representations by stacking together multiple smaller representations. So for example, we can repeat 4 times this basic representation. There's also like a shortcut if you want to pass a list, right? That doesn't matter too much. And we can verify that the result is 4 times larger than the basic representation. Okay, so this was the direct sum. Now we pass to the next concept, that is the one of regular representation. You should maybe have already heard of a regular representation in the lecture. This is a especially important representation because it's the one we're going to use to link steerable CNNs later with group convolution. But let's get to that in a couple of steps. Essentially, the regular representation, you can imagine it's the representation of the group acting on the vector space of functions over the group itself. So let's stick for simplicity to the case where the group is finite as a just to start. So basically, the order of the group, right? So we write it this way, is smaller than infinity. So it's just an integer. And think now of a function over the group, right? As a real function as essentially a vector space which contains one dimension for each group element. That's kind of the same way you would, try to store it. If you want to implement it on a computer, right? A function over a finite number of elements, you would just store a vector of the same size, right, of your set, and each entry would represent the value of your function, right, on one of those elements, right? So you can imagine this is literally what is happening here, right? We just associate one of each of the dimensions, each of the axes, right, of this vector, right, to one group element for any arbitrary choice of order of the group elements, right? We just associate to each group element a number, right? And this vector space, which is of course has dimension equal to the size of G, right? Actually carries a representation of the group element, because now we can look at how the group itself, right, translates functions, and we can turn this into actually a permutation of the entries of these vectors. Let's try to see that a bit more concretely. First of all, we define the action of the group, right, on these G-dimensional representations by first thinking about functions, right, that are from the group elements into R, and we define the function f rotated by G by just taking the original function f and evaluating it on the point H, but shifted by G. This is kind of the same equation that you usually see when you take a function over time, right, and you shift it by a certain delta x, I don't know, the way you would write it would be f of x minus delta x. That's your function shifted by delta x. It's just that now we generalize it to arbitrary transformation, not necessarily like a delta in time, right? But an arbitrary transformation g, which could be a rotation, could be a translation, and we just refer to its inverse as a -1, right? Rather than just having minus delta x. But think about this in the same way you would think about shifting a function on the real axis. So, okay, the point is that now this function f, we can represent it actually as a vector, right? So we want to, the goal we want to, essentially what we want to do now is turning this equation, right, into a matrix that permutes the entries of this vector. As a side question, but I leave this for you to try at home. You should try to prove that the space of functions on the group is actually a vector space. So I kind of assumed it now, right, that we associate to each group element an entry in a vector, right, and this is a vector space, but you can try to prove that yourself. So we'll move over this. I think it's easier to just see what these matrices look like rather than trying to construct them manually. So let's go back to the example with the group of 8 rotations. So this, again, was the group of the cyclic group of order 8, right? Which essentially contains rotations by 2 pi over 8 and its multiples. And the regular representation, we can verify immediately it's of size 8 because it acts on a vector space, which has, again, one entry for each group element. And we can try to see that, of course, the representation of the identity is the identity matrix. Intuitively, right? If you shift your function by the identity, it means you're not shifting your function, right? So your 8-dimensional vector is mapped into itself. You just multiply it by the identity matrix. What happens if we actually multiply it by the representation of the rotation by 2 pi over 8? Before looking at the solution, try to think about the fact that this rotation, right, shifts in a cyclic way, right? Each group element by a step of 1. If you remember maybe some modular arithmetics, right? This is essentially the same group of modular arithmetics modulo 8. So a shift by 1 always moves you one step further, right? Until you reach 8 and you start again from 0, right? And this is implemented by this 8 by 8 matrix. Maybe it's not rendered super nicely because there's a few minus and 0 point, but you can see this is just a cyclic permutation of the 8 entries by a step of 1. So the first entry, right, after you multiply by this matrix, is moved to the second one. The second entry is moved to the third one, and so on and so forth, until the last one, which is moved back to the first entry. So the representation of the element 1 is just a matrix that permutes all the entries by moving them one step in the next position and cyclically back to the origin. Yeah. And of course, we can we can now look at one specific function just to see if this makes sense. So imagine that we build a function that is 0 over the whole group, right? And it's 1 at the identity. So as we said before, right, the way we would do this is by creating a NumPy array, right, of dimension 8, and associating to the 0th entry the value 1 and 0 to all the others. That's a way to represent our functions. We check that now if we want to shift the function by the identity, right, which of course give us the same result, we can multiply it by the representation of the identity, which again give us the same vector. That kind of makes sense, right? Now, if we instead multiply it by the representation of the first group element, right, we actually see that the one that was at the identity has been shifted to position 1. And more generally, if we multiply by the representation of the, I don't know, 6th element, we shift the function by 6 positions. Does it make sense? Do you see how these cyclic shifts are actually implemented as a permutation matrices? And hopefully it also makes sense that these permutation matrices can also be combined with each other, right? So rather than shifting by 1 and then shifting by 6, we can shift by 7, right? That kind of makes sense, right? Okay, yeah, this should give you an intuition about what the regular representation is, and maybe you can also try to connect this with what you have seen with the group convolution, where the features of a group convolution neural network was essentially quite similar to this vector, right? You have like a big tensor, right, containing for each group element an activation, right, which you can interpret as a function over the group, right, just stored as a NumPy or PyTorch array, right, with one element, one entry per group element. Yeah. Okay. You can prove this, but you can try this at home. So let's go further. Okay. One more concept we need to introduce is that of equivalent representations. Essentially, represent two representations of the same dimension, D, right, are considered equivalent when they basically differ only by a change of basis. So we can take a representation left and right multiplied by some matrix Q, right, which is invertible, right, and we obtain a new representation rho, right, rho and rho prime. We consider them equivalent. So you can imagine that they essentially model the same type of transformation, but just in a different basis. They just differ by the choice of basis for the vector space they operate in. Do you see what this means? Is that clear for everyone? Okay. So yeah, you can verify that this kind of makes sense in this way. Let me skip over some details and go further. This also allows us to build, this gives us another tool to build more complex representations, because now if we want to build a d-dimensional representation, we can take a bunch of smaller representations, combine them with the direct sum, right? And then apply a change of basis on top to get a more complex representation. So this is done by, for example, combining two trivial representations, two regular representations. We just take the direct sum of them, right? And then we apply a random change of basis to this. And this generates a new representation rho, which is, of course, 18-dimensional. Does this construction make sense for everyone? Okay. So this construction with a change of basis is actually much more useful in the other way around. We usually don't want to start with some representation and add a change of basis, but we rather start from some complex representation and try to boil it down to smaller representation by finding the right change of basis. Yeah? You have a question?
Why would we want to build something out of trivial representations?
Yeah, that's a good question. We are gonna see that in a second. But that's so it's not really common to start from many trivial representation to build something bigger, because it might be not really interesting. It's more interesting to do the opposite. So you start from a big complex representation, right? And you actually try to see if it actually decomposes in smaller representations once you find the right change of basis. So this is the topic of the next section, indeed. And I'm going to talk about irreducible representations.
Can I add to it?
Yeah.
Like, in your neural networks, you often have to specify what kind of objects am I dealing with. And if you maybe if your input is a vector field, then it's transformed by a what we call like a type 1, a frequency 1 rotation matrix. So that's a specific representation of the rotation group. But your input could also be like heat, or temperature, right? And that doesn't rotate, so it has only a trivial representation associated with it. So if your input to your feature map, suppose you model climate data, which consists of both vectors and temperatures and maybe pressure, then indeed, like the vector that's transformed by rotation matrices, temperature trivially it doesn't rotate, and pressure also not. So this is an example of why you would specify it, and what we're going to see next. And once we have specified, how are we going to process this? Yeah,
and also as a very simple example, like whenever you work with the images, right? Just natural images, the colors, right, of an image don't rotate, right, when you transform the image. So that's an example of where trivial representations are useful. But yeah, so in general, they come very often as actually type of representations that describe your raw data, right? So it's very common to find them. And the nice part about this trivial representation also is that it turns out to be an irreducible representation. That's another nice property. Let me first define what is an irreducible representation. but kind of as the name suggests, irreducible representations are those which cannot be decomposed further in this way, right? The representation raw here, right, is not irreducible because we can find a change of basis Q, right, such that it can be actually written as a direct sum of smaller representations. And irreducible representations are those representations which cannot be decomposed further. And you can imagine that, yeah, trivial representation is like so simple, like it cannot be written as anything smaller. It's already one dimension, so you cannot go lower than one dimension. So that's the simplest example of trivial representation. But there's many more. And as a spoiler, we will see that these irreducible representations are actually what we use to define a Fourier transform. They give us kind of the equivalent idea of frequencies of cosine and sines that you would use to define a normal Fourier transform. Some notation, irreducible representation is a very long word, so usually we shorten it to IREPS. So you will see often the tutorial using the word IREPS for simplicity. And some more notation. We usually refer to a group as G and the set of all its irreducible representations as G hat. This is just a set which we can index, right, containing the set of all irreducible representations. Generally speaking, you can assume that for most of the groups we care about, irreducible representations are actually well known, right? So those are a few small, well-known representations that we can compute, and they give us essentially the building blocks to construct more complex representations. Let's see a few examples. So again, as I said before, the trivial representation is an irreducible representation. We verify this by checking basically the IREPS of the group G. Basically, this function returns us the group elements as indexed here, right? So we see that basically the first IREP of our group is equal to the trivial representation. Not much more to say about it. We can verify that as Eric mentioned before, what he referred to as frequency 1 IREP is actually equal to the standard representation of the rotation group. So before we computed, we defined. Okay, I did not check it here, but basically you can check that IREP1, which is returning your two-dimensional representation, which actually is equal, which contains the cosine minus sine, cosine and sine of this angle, which is the group element. So that's just a standard representation of the group G. And yeah, as we have already mentioned, the idea is that now we have all these irreducible representations, which we can use to now build much more complex representations. We can go back to the previous construction rather than concatenating generic representations. We can always build any possible representation by basically choosing what irreducible components to use. Stack them together and then apply one change of basis. And that generates every possible representation. That's quite convenient because now when we want to build a neural network with one specific representation, we can actually simplify the problem to, rather than looking at every possible representation, which is quite complex, we can always just decompose these representations in irreducible components and solve every problem at a smaller scale by looking just at these irreducible elements. And yeah, so you can actually, this is also how representations are built internally in the library. So whenever you work with a representation, you can actually access also the irreducible representations it contains. That's as a side information. But yeah, the next step is checking the only non-trivial representation we have seen so far, which is the regular representation. The regular representation is quite a large representation, and it turns out to contain a lot of irreducible representations. So let's see again at the example of the group of 8 rotations. That was an 8-dimensional representation. And if we now check its IREPS, we see it contains all IREPS from 0 to 4, which for this specific group essentially corresponds to the frequencies 0 to 4, all the rotational frequencies 0 to 4. Okay, imagine that the frequency 0 was the trivial representation. That was quite simple. We saw it. The frequency 1 was the standard representation. So it's all 2x2 rotation matrices that just implement your rotation. And then the frequency n is just basically obtained by, instead of rotating by theta, by rotating by n times theta. And that kind of corresponds to this idea of frequencies that we mentioned earlier. Let's see that a bit more precisely. So first of all, we can also access the change of basis of the regular representation. So we see it's this matrix. This matrix is going to be quite interesting. So let's go back to this in a second. But let's look at these specific IREPs. So first of all, we look at the first IREP in the regular representation. This was the frequency 1, right, IREP. We can actually instantiate it explicitly and check that this indeed contains a rotation by, what was it, 2 pi over 8. We can now try to manually construct the regular representation using this equation by actually stacking all the IREPs and applying the change of basis. So this is pretty much what we do here. For each IREP in the regular representation, we instantiate the IREP, right? We evaluate it on one specific group element. Then we basically use SciPy to build this block diagonal matrix. It's just a nice, convenient way to just build in a sparse way this big matrix which contains all the IREPs in the diagonal. And then we can, well, first of all, check the regular representation. We check this direct sum, which does not have the change of basis yet, and we see it contains all the IREPs of different frequencies. So this is frequency 0, this is frequency 1. You can verify this is frequency 2 by actually multiplying this matrix by itself twice. This is frequency 3, which is obtained by multiplying this matrix here 3 times by itself. And then there's a frequency 4, which is a bit ugly because this is only one dimensional. That's because 8 rotations, if you take any rotation, any of these 8 rotations and you apply it 4 times, you basically don't have, like, the sign is always equals to 0, so you don't have to actually store it. So this is kind of related to the notion of aliasing, if you're a bit familiar with harmonic theory, but just ignore this. This is more like a technicality, so it doesn't matter so much. The general intuition that this is rotating with frequency 4 still holds. Yeah, finally, we just check that if we now apply the right change of basis on the left and the right, we get back the same matrix we had before, which turns out to be the case, fortunately. Okay, so this was a bit introduction on representation theory. I think that this kind of covers all the building blocks we need to work with representation and representation theory. What we're going to do next is try to interpret what these matrices and what these irreducible representations are, to connect them with the Fourier transform, as you can already see there, which we can then later use to build steerable CNNs. But before maybe I go into this part of the tutorial, do you have any question? Is everything so far clear? Essentially, what we did so far was throwing a bunch of definitions, which I know is will be quite heavy, so, and you have to try to keep all of them in mind to use them in the next part. So, yeah. Irreducibility.
Yeah, this is like why I think
yeah. Irreducible.
Irreducible.
Yeah.
But is it it must be something else. Particularly we have like all the different.
So I think that, well, the next section is going to give you a bit more intuition about what these irreducible representations are, like from in more concrete terms. I think that at the moment you can stick with the idea that a group has many different representations, and you can start from them, decompose them, right? And at some point you cannot decompose them anymore, and you are left with some small building blocks, which we call irreducible. That's essentially how they are defined. From a more intuitive point of view, as we have already seen for the cyclic group, this essentially corresponds to the harmonic functions over the group. So, for example, for the group of rotation, these irreducible representations are essentially the cosine and sine of different frequencies. It's still a bit unclear so far because we see them as matrices, but this is the topic of the next section. Try to make them look more like the typical harmonic functions. So yeah, trust me on that for 5 more minutes. Anything else? Okay, then we can move on the Fourier transform. Okay, so let me first spend 2 words about the Fourier transform. We talked about before the space of functions on the group, and we said this is a vector space, right? And if you recall from your course on linear algebra, you can pick arbitrary choices of basis for a vector space. So if you have like you have a vector space of dimension D, you can apply any change of basis, right? And now you have like a new way to parameterize essentially vectors in this vector space. And the space of functions is not different from this, right? So typically we represent functions as by storing one value, right, for each point in the space, right? So for each group element. But this is actually just one of the many possible choices of basis for the space of functions. And the Fourier transform is nothing else than a change of basis in this space. So rather than expressing a function by explicitly storing its value on each element, right, we express a function as a linear combination of other functions. Does it make some sense? You start seeing some intuition here. So before like going into the tutorial, let me spend 2 words maybe on this. If you remember maybe from machine learning, when you did the linear regression with a non-linear basis function, right? That's kind of a similar idea, right? You have you predefine a bunch of fixed functions, which are non-linear, right? And then you learn some parameters with linear regression, right? To linearly combine these functions. And that generates a new function, right? Which is non-linear, right? The way you can think about this is rather than, manually learning a different value for each point in your dataset, right? You learn a bunch of coefficients that allow you to linearly combine a number of predefined functions, right? And that allows you to parameterize more generic functions over your dataset. You can imagine that's quite similar like with a Fourier transform, rather than storing a value for each group element, which would be kind of the same idea of a point in your dataset, right? You instead take a bunch of functions, so sine and cosines of different frequencies, you pre-compute them, and now you only learn a vector to linearly combine these functions. And yeah, that's kind of the same idea. And what these basis functions we defined, so these sine and cosines of different frequencies, those are basically the columns of your change of basis matrix. Do you see some intuition here? Is it kind of making sense for everyone? Okay, so we can go back into the equivariance part. So essentially what we need to use is this theorem, which I'm not gonna state very precisely, but you can basically take it as a generalization of the definition of a Fourier transform. And this theorem essentially tells us that any representation, any orthogonal representation of a compact group can be decomposed into irreducible representations. That's kind of what we saw so far. And in particular, the regular representation is decomposed, the decomposition of the regular representation contains precisely every irreducible representation of the group. So whenever you have the regular representation, you know that you are actually using all the existing irreducible representations. So that also starts to answer a bit the question you had before about what are the irreducible representations, because now you can see them as actually subspaces or components of the regular representation. And so that also should suggest that somehow they encode everything there is to know about how the group is represented, because the regular representation literally encodes the way you combine group elements. So it has all possible information about it. I will use for simplicity a different group now, because the cyclic group has some annoying properties we will see later. So we will use the dihedral group, which is equal to the cyclic group of 8 rotations, but it also includes mirroring. So rather than being 8-dimensional, is 16-dimensional. Just think about 8 rotations and a reflection followed by 8 rotations. So that gives you 16 possible transformations in total. We can access the reflection element like we did for the identity before. We can access like a rotation and reflection using this notation. So this is just a rotation with 0 reflections. This is a rotation with also a reflection. And we can, of course, combine group elements like before. If I kind of assume that you are a bit familiar with the structure of the dehydrator group, because maybe you've seen it also for a group convolution when you were trying to build a network that is equivalent to 90 degrees rotations and mirroring. But yeah, doesn't matter so much. It's just a slightly different group. Okay, so now we can go back to the Fourier transform. I will state this first as it is, and then we try to make sense out of it. Basically, the Peter-Weyl theorem gives us a way to define a Fourier transform for functions over the group in terms of rather, sine and cosines over the time domain, right? Instead, in terms of the entries of the reducible representations. So if you have a function f, right, you can always express it as a linear combination for a certain choice of parameters of the entries of the reducible representations. Think about a irreducible representation as a map from a group element to a matrix. But now, if instead of looking at the full matrix, right, you look only at one specific entry of the matrix, that's just a normal function over the group, right? So the entry nm, right, of the irrep rho j is a scalar function, right? It maps each group element to a real number, right? So basically, what we do is picking every possible irrep and every possible entry of each irrep. This provides us with a number of functions, right? Which, for example, in the case of SO2 would look like the typical sine and cosine with different frequencies. And now we use them to basically linearly combine them to construct a new function. I like to bring up again this example with the linear regression, right? In linear regression, you kind of try to optimize these parameters, right? These weights, right? And you have these basis functions fixed, like, I don't know, sometimes you use polynomial functions. You can use sine and cosines as well for linear regression, and that allows you to model more complex functions, right? Does this analogy make sense for everyone? Yeah? Yeah. Yeah, that's a good question. Yeah, so this is where the analogy breaks, kind of. So thanks for pointing that out. Like, the point of a Peter-Weyl theorem is that all these functions are actually orthogonal to each other, right? While, when you do linear regression, you have the freedom of choosing whatever function you want. So you can also choose non-orthogonal functions. So that's a good point. What I want to convey here is more the idea of what is a space of functions and what it means to linearly combine functions to generate new functions.
How about duplicate entries?
Yeah.
The cosine,
That's the reason why I use the dehydrator group now, because in that case, it's not a problem. But with SO2, you do have some duplicates. That's coming up in the next section. I avoided that on purpose to keep it simple. But yeah,
so
you have to
there's no duplicate.
Precisely. So Peter-Weyl theorem tells us that there's never any duplicate entries when you have actually complex matrices. But we do deep learning. We don't like complex numbers, so we use real representations. And in this case, Peter-Weyl theorem tells us that there's almost never duplicate entries, except for a couple of edge cases. And unfortunately, SO2 is one of those edge cases, and also the cyclic group. So we're going to deal with those later on, but you have already seen that the rotation matrices contains the cosine twice or the sine twice. So that's something we have to be a bit careful about. But we will ignore this problem for the next 10 minutes, so don't worry about it. Let me get back to the definition of a Fourier transform. So okay, this is essentially the definition of an inverse Fourier transform. Here we start from a bunch of coefficients, which we kind of interpret as the Fourier transform of our function, and we go to our function evaluated on each group element. We can actually reshape this equation a bit more, just to make it a bit look a bit nicer. We don't like this loop over all the indexes. So we use this property that the trace of the product of these two matrices, right, is actually equal to the sum over their entries. So like if you take the matrix A and B, you reshape them as vectors, like with the numpy.reshape -1, or like numpy.flatten, right? And then you take the inner product of these two vectors, right? This is the same as taking the trace of this matrix product. You can verify this again. This is one of the things you can try at home to check, but for the moment you can kind of trust me. The nice part is that this allows us to write this ugly sum in a cleaner way. So we can rewrite the same sum here, rather than summing over M and N for the weights and the entries of the IREP. We just write this as the trace of the IREP, right, times this matrix, which contains these entries, right? And yeah, that's pretty much it. And that allows us to basically call this function, right? Now it's a function from IREPs into matrices. This is what we typically call a Fourier transform. And you know, in a normal Fourier transform over the real line, you would associate to each frequency kind of an energy and a phase. You can imagine that this energy and phase are here stored as matrices for each IREP. So in the case you have like a real line, IREPs are a bit simple. There you just need to have like a magnitude and a phase. For general groups, this is a bit more structured. So you need more general matrices, which could be, you know, 1-dimensional, 2-dimensional, or n-dimensional. So that's the kind of generalization. And yeah, we can also go, you know, the other way around. This is a linear transformation, so we can take the inverse to basically define the actual Fourier transform. So starting from basically the function f, we want to actually compute the weights. This is just done by taking the product between two functions. So this is a rho j mn is a function over the group. Your function f of g is a function over the group. You just take the sum and you average over the product and you average over the whole group. And that gives you the weights. And this is essentially what we define as a Fourier transform. In a normal Fourier transform, you would do essentially the same, just in a continuous way. Replace this IREP with your complex exponential or the cosine if you do it in the real space. And that would be literally your normal Fourier transform. Up to some normalization. These you can ignore all these constant terms. Those are just needed to basically make sure that the linear operation we are doing is not just a invertible matrix, but it's also an orthogonal matrix, which often makes things a bit cleaner. Yeah, so far so good. Okay, cool. So maybe this also gives you finally answered your question about what are irreducible representations, because you can literally define irreducible representations in this way. And these are basically the harmonic functions over the group of interest. So if you have like SO2, right, which is like a circle, is equivalent to a circle, these irreducible representations are basically is an orthogonal basis for functions over the group, which also happens to be basically equivariant. So if you rotate the group as this function rotates, because they satisfy the representation properties we said before, but that's essentially the idea. And if you go to more general groups, like the group of 3D rotations, you may find Wigner-Eckart matrices or spherical harmonics, if you're a bit familiar with the representation theory of SO3. But yeah, that's pretty much the idea. If you are not familiar with the representation of SO3, don't worry about it. You're going to see that probably in the next tutorial. So let's just stick to the simple case of SO2. Okay, so that's it for the Fourier transform. We can play a bit with it. We can take a group and check all its IREPs. This function returns you the list of all the IREPs. Yeah, this is the same check we did before, right? The trivial representation is equal to the first IREP. In these questions now, I'm asking you to implement essentially these inverse Fourier transform and these Fourier transforms by using basically all the tools I provided you. So you have access to the IREPs, you have access to the regular representation, you can combine IREPs, so you can try that yourself. I have already the solutions, and I don't know if it's really worth going through every line of code, but you can see it's not really complex. You just have to instantiate every IREP, right? Sorry, this is the Fourier transform. So basically, you take every IREP, yeah, you instantiate it, you evaluate it on the group, on each group element, right? And then you basically apply the projection over your function. So that kind of this product essentially implements, this average over the group, right? You have to weight appropriately, right, all the terms to make sure it's normalized, but that's pretty much it. And then you have to do the inverse, which is, well, again, just about implementing the previous equation. Yeah, I would encourage you to try that yourself, but it's not super complex. And yeah, finally, we can check that these operations are actually inverse of each other. So if we take a function, we take the Fourier transform, then we take the inverse Fourier transform, we kind of expect to get back the same function. The nice part, and the reason why, well, in the last hour we talked about all this stuff, right, is that this becomes quite interesting when we go beyond discrete groups or finite groups, because what we did so far was quite easy. We can, iterate over all the group elements. It's not giving us so much more than a normal group convolution. This becomes quite nice when we actually use infinite groups, where we cannot really store the regular representation by storing each group element and its own value, right? But a Fourier transform allows us to, rather than discretizing the function by only evaluating it on a subset of the group elements, we can now discretize it in the Fourier domain by only taking a subset of the IREPs. That's, again, kind of similar to what you do with linear regression, right? Rather than manually storing a function, a value for each data point in your dataset, which requires a number of parameters equal to the points in your dataset, you try to fit a smaller function, right? So a lower number of weights by predefining only a few basis functions, right? And then learning how to linearly combine them. That's kind of the same idea, rather than using every possible IREPs, which are going to be infinitely many, because the group is infinitely dimensional. We only pick a subset of them, maybe up to a certain frequency. So we only use a frequency up to frequency 3. So we have only 0, 1, 2, 3. We only learn ways to linearly combine these coefficients. And now we have a function which is over the full group, but we only need a finite amount of memory to store this function. And because of the properties also of these IREPs, right? All of this is equivalent. So now we can actually rotate the function in the infinite dimensional space, which we are not actually representing. And that's equivalent actually to shifting the coefficients of the Fourier transform. If you are familiar with the harmonic analysis and Fourier transforms, you may know that if you shift a function in the time domain, that's the same as rotating the individual complex numbers in the Fourier transform, right? That's the same property we also have it here. And that's why it's convenient to work with these objects. Again, here, as an exercise, you should try to implement the Fourier transform for the group O2, which is the group of continuous rotations and reflections. But of course, you cannot do it for every possible group element. You cannot do it for every possible IREP, because there's infinitely many of them. So what you're going to do is only do it for a finite subset of the IREPs. You can play with that yourself, but I'm going to skip over this. We can try to plot this and verify that all of this makes sense. So what we do now is discretize this group with only 100 rotations, just to be able to plot it. So that includes essentially 100 rotations and 100 rotations and reflections, right? And we take a random function. Where did I generate it? I generated a random function in the Fourier domain. So for frequencies only up to frequency 3, I generate a random Fourier coefficients, right? For each IREP, I store this as a dictionary. This generates a random function, right? Which is, we say, band limited only up to frequency 3. So it has no coefficients with the frequency above 3. And then we can try to take the inverse Fourier transform you implemented above to evaluate this function on every group element in this discrete grid we built. So we can try to plot it. So this is the value of the function over the rotations. And sorry, this is over the rotation. This is over the rotation reflections. And yeah, that's cool. This is a continuous function over, our infinite group, but it has only a finite number of parameters. What we verify, yeah? Oh yeah, because like O2, right, is as I said, right, we have like 100 rotations and 100 rotations and reflections. So like imagine these are two different domains, right? We have 2 times every rotation, right? So to plot it in a nice way, I plot it as a function from 0 to pi for just the rotations, so the blue line, and then for the corresponding function on the rotations and reflections, right? I plot it again as a separate line with a different color. Yeah, exactly. Yeah, yeah, you can imagine. Yeah, you can imagine that essentially the group of O2, right, is from a topological point of view, is equivalent to 2 copies of SO2, right? Like that's like you can try to draw it, but you can identify every group element as R theta, right? Times so this is a rotation by theta, right? Between 0 and 2 pi, times a mirroring, a flip, right? Which can be there or not, right? So this is either this or this. Right. So those are all the elements of O2, and with theta in 0 to pi, right? So okay, so basically the function is taking values on both of these domains, and this one we can kind of imagine as a circle, right? So the angles between 0 and 2 pi, and also the elements of this, right, can be imagined as being parameterized only by theta, right? So this is a separate circle, right? So these are, I don't know, elements in here, so elements in a separate circle. This is equivalent to SO2, right? This is equivalent to SO2 followed by a reflection, right? And then we just plot it as 2 different functions over these 2 different rings, essentially. It's just for a plotting purpose. Don't worry about it. Yeah. So yeah, we can try to generate more complex functions by adding more frequencies. So before we add up to frequency 3, we can see that if we add frequencies up to 8, get a bit more complex function. It has sharper edges. I don't know. It's much more expressive, of course. There's many more parameters, but it has, indeed many more parameters. So it requires more space to store. Regardless, it's still like a continuous function over the full group, which we can easily represent with a finite amount of memory. So this introduces some kind of trade-off that we have. We can choose of how many frequencies we want to represent, similarly to the trade-off you have in a linear regression, where you can choose how many basis function you want to include. This is the property I mentioned before. Like in a Fourier transform over the real domain, if you shift your real function, that's equivalent to basically rotating all the Fourier coefficients. That's the same also for in our case. If we translate our function, this is with the regular representation that we saw before. This is equivalent to basically transforming the Fourier coefficients by multiplying them with the corresponding IRAP. This is missing a row of J. It's a typo. Sorry for that. This is something you should prove at home. It's not too complex. But for today, you can trust me. And the nice part is that we can actually try to visualize this. So now let's generate again a random function. We basically, we try to plot it, and then we sample a random rotation G, right? And we try to shift this function. We can do that by multiplying every coefficient, right, by the corresponding IRAP. So the coefficients at a certain IRAP row, right, are multiplied by the matrix representation with the row of this group element. And now we plot it, and we see that this is indeed the case. This was our original function. This is the shifted one. So the group element is a rotation by 0.49 radians. So it should take this blue function and shift it to the right by this angle. So hopefully this is what happens. So you should see that maybe these 3 peaks are moved by about 0.5 on the right. Conversely, the orange one is shifted in which direction? it should be, yeah, okay, it's the same, right? Yeah, it's also shifted on the right. Yeah, so you have this rotation, this orange line. Maybe you can try to follow these two peaks. They are shifted. They're still aligned here. Yeah, I don't know. This is just again for visualization purpose, and just to prove you that these coefficients actually transform according to the IREPs. Okay, so is this part clear so far? Now we can try to.
Want to check like
Mhm.
how much is up there?
Yeah. Yeah, I think that's if you leave me finish this section, then we can take a coffee break. Because that concludes the part about representation theory, and then we can go on training some networks. So the second part is a bit lighter, hopefully. So yeah, 2 minutes to close this section here. Okay, so now this property we just proved, right? So that we can rotate the Fourier coefficients, right, by multiplying with the actual IREPs, and that's equivalent to shifting the function, is the essential property we need to use to build equivalent networks later. So let me first try to connect a couple of dots here. So let's try to look at the Fourier coefficients. Right now we store them as essentially a dictionary, right? Which for each IREP stored a different matrix containing, again, the Fourier coefficients. And each of those matrices was transforming according to its own IREP. What we want to do now is instead look at all these matrices together as a unique vector space. So we try to essentially take, for each IREP, we take the corresponding matrix, we vectorize it. So vectorization, let me write it. It's essentially the dot flatten that you do typically in NumPy. If you have like a matrix A, B, C, D, we vectorize it by writing just A, C, D, D. Not that with respect to NumPy does vectorization row-wise, while here we want to do a vectorization column-wise. You see that this is the first column, this is the second column. And the reason why we do this is that if this matrix before was transforming according to one IREP, when we were multiplying it on the left, that means there was a matrix here, right? Which was a row of G, right? Which was multiplied by the columns of this matrix were multiplied by this one. If we vectorize it in this way, you see that now you have two copies, two-dimensional vectors, and each of them is independently being multiplied by a copy of this. So kind of the intuition here is that here you have the matrix transforming according to this IREP, while this four-dimensional vector now transforms according to the direct sum of this IREP times plus itself. Right? So this direct sum, right, we'll just take this matrix, repeat it twice in the block diagonal, such that when you multiply by this vector, we're just taking this times these two enters, and then this times these two enters. Does it make sense? And now we can do the same. So we do this basically for each IREP, and then we start stacking also these vectors for each different IREP. And that gives us a very large vector, right? Which contains all the Fourier coefficients. And yeah, that's pretty much the idea. And then what you see here is what I did here on the whiteboard, right? So now we ask, how does this vector transform when our function is shifted? So when the function is shifted, each individual Fourier coefficient is transformed by the IREP. So when we stack everything together, the final result, right, transforms according to this direct sum of IREPs. So again, for each basically IREP, you take a copy for each of the columns, right? So for a number of time equals to its own dimension, and then you stack it for each possible IREP. Right? I said IREP a lot of times. I hope this message is clear. But yeah, that's pretty much the idea. And what we did by doing this process is actually building the regular representation. So now we can kind of close this topic. What we said before is that the regular representation essentially contains all the IREPs, and you can kind of see this here because it turns out this construction here is equivalent So it's an equivalent representation to the regular representation, and the change of basis that relates this direct sum with the regular representation we built initially is precisely the Fourier transform. You can try to prove this yourself, but yeah, the metrics we saw before, so when you build a regular representation and you take a change of basis, that's going to be a very large matrix Q, which implements in a more implicit way all these functions you built yourself earlier, which were taking these inverse Fourier transforms. But by doing that with the right indexing and the right coefficients in the matrix. So that's basically all we need to know about Fourier transform and regular representation. I don't want to keep this too long. So if you, yeah. Mm-hmm. So in theory it does not, because like this actually works even for infinite groups, right? And that's kind of the intuition there. You can do this, right? For infinite groups, the point is that this sum is indexed by an infinite dimensional set, right? So it's never going to stop, right? It's going to build a representation which is infinitely dimensional, which of course we cannot store on a computer, right? So I think the intuition works a bit in a nicer way when you look at finite groups, because you can imagine this is a for loop over like a set of indexes, and you can implement, that's the for loop you implemented before, essentially, and that builds a matrix, right? But in theory, you can, like mathematically speaking, this actually, this works for infinitely dimensional groups, for compact groups only, but you can do that. And in practice, as we said before, right, for infinite groups, we just put manually a threshold on the maximum frequency. So we turn this infinite dimensional representation, right, into a finite dimensional one, which approximate functions to a, in a kind of coarser way. Yeah. Yeah, I think that this is a good moment to take a coffee break. So, yeah, see you again, I don't know, 5 minutes, 10 minutes?
Yeah, let's aim for 5 minutes or so. Just get coffee and maybe see everyone is back then.
Should I maybe pause the recording?
Oh, yeah.
Okay. Hello, everyone. Shall we restart? Okay. I promised I would go to the neural networks now, but I just want to mention this quickly because Eric asked it before. What happens in those two cases where we have redundant entries? It was, for example, for SO2. That's the reason why I ignored SO2 before. Let's not go too deep into this, but like I just want to point out that in this case, the IREPs are a bit redundant. You see that if we look at the entries of this matrix as basis functions, we have 2 times the same, like cosine appears twice and sine also appears twice, right? There's not so much to say about this, except for in this very specific case, let's just not take all 4 of them, but just 2 of them. And that's pretty much everything. So you can prove that basically rows are always orthogonal to each other. At most, it can happen that one column, right, is containing redundant entries. So we just need to literally remove the second column because we don't need it. But then the rest of the theory stays the same. So when we do a shape, rather than taking the 4x4 matrix and turning it into 2x2, turning it into a 4-dimensional vector, we just remove the second column completely, and we just keep the first one. So we are left with 2 entries, which still transform this IREP, right? And that's all of it. In general, from coding point of view, you don't need to worry about it because the library is taking care of that already. So, it's just for you to know what happens in this case. But generally, you will always in the library call something like band limited regular representation up to frequency, for example, 7. And this is going to return you basically this, what is it? This direct sum of IREPs up to frequency 7, right? So you don't have to worry about the fact that some of those irreps may appear a few less times than expected. So that's the only difference. And yeah, that's pretty much everything. You just rely on this call whenever you use the library. In the previous exercise, you have to code it up yourself. That's why we ignore this edge case. But that's everything. Okay, so after this very long introduction, we can move on the neural network part. Yeah, unfortunately, like this took a bit longer, so I cannot really go maybe step by step on everything. I will try to go a bit faster and go to the point. But let me at least give a brief overview of Steerable CNNs. Again, you should have seen them already in the lecture, so hopefully you already have an idea. I want to show you how what we did so far fits in the framework here. In a Steerable CNN, okay, let's start from a group convolution. In that case, you take, for example, filters, you apply every possible transform versions of them, and you generate a feature map which has an activation for each group element. The step we do here, right, from group convolution to Steerable CNNs is by, instead of applying a filter every time for each group element and store an activation for each group element, we are going to replace the part of the tensors that store activations for each group element, for G being like the subgroup of rotation, with instead the Fourier transform that we defined earlier. So when you build your group convolution, like typically you would basically store the activations as a tensor, which has, for example, for 2D isometries, it would have like some resolution for the pixels, right, as a normal CNN, and then it would have an additional dimension where you store also activations over the rotations, right? So rather than having, for example, a three-dimensional tensor with a number of channels times the two spatial dimensions, you would have a four-dimensional one with a number of channels, number of rotations times the pixel grid, right? What we do here is noticing that this second dimension with containing an activation for each rotation is actually the regular representation we saw before, right? And now basically the trick is replacing this dimension rather than with the regular representation, which had a discrete number of elements. We replace it with this band delimited regular representation we used in the last half an hour. And so that allows us to reinterpret the features of a neural network rather than as basically scalar function over the group. It gives us this interpretation as basically vector field over instead the base space over the pixel grid. So we don't think about basically our tensor as a set of activations for each pixel and each possible rotation, but rather as a vector transforming according to the regular representation attached to each pixel. And that's what we define as a feature field. Yeah.
Like in my slides, I use the capital G mostly for the entire
All right.
group, but like rotations and translations, but here G is like the subgroup, like O2 or S2.
Yeah.
So F is a function of Rn times G. You should think of it F as a function over both the translation and rotations group, giving to each group action a scalar feature value. But now, yeah, Gabriele is making the factorization of the method from Rn to a vector space that is transformed by G.
Yeah. That's yeah. I know it's quite confusing. Sorry for that. But like this is just to stick to the notation we used in the previous section. I used G to refer only to the O2 or like just a group of rotations, such that we can be consistent on that. But yeah, sorry, it's not consistent with the slides. But yeah, I'm sure you're going to be able to figure that out. I'm leaving this as an exercise for you to derive basically the connection between this formulation and the normal, the one in group convolution, and what are the right actions. I think this is quite useful to understand what's happening. I want to move slightly faster here to go to the point. So yeah, the takeaway here is that we interpret features of a neural network not anymore as just invariant or scalar functions over the pixels and the group, but rather as vector fields over the pixels only. And the single vectors, as we're going to see in the next step here, are basically transforming according to some representation, which is the regular representation. So now what happens is that our function is a function from the pixels, right, into some set of channels. And when we rotate our function by, for example, some g, and we shift it by x, but the shifting by x is the same, but the rotation by g moves the pixels and then rotates the channels by this row of g. In the case row of g is the regular representation, this is exactly the same as what you had with the group convolution, because this row of g would just permute the channels, which would before encode the function over the rotations. Just think about this row of g as the permutation matrices we saw before, right? But this kind of formulation is now a bit more flexible, because we can replace this row and make use of other representations. So, for example, the band limited regular representation for a continuous group. That's pretty much the intuition behind the steerable CNNs. Is that making sense for everyone? I think that Eric has also a bunch of nice visualization of this. So, take a look again at these slides. Okay, here you should derive basically this connection a bit more precisely. But yeah, try this at home as an exercise. Okay, now we can look a bit more generally at steerable CNNs. As I said, like the step from group convolution to steerable CNN is replacing this group dimension with a regular representation. But we can go further. We can replace this now regular representation with any representation. We are free to choose any. So simple choice would be, for example, to take the trivial representation, which we defined at the beginning. That's basically giving us one single channel that does not transform. So if we choose as a row in the equation here, right, the trivial representation, this function f now models basically simple scalar functions that don't change. Like, for example, think about this bean with these blue balls as a, just a colored image, right? When we rotate this image, right, we just move the pixels, right? But we don't change the color of the image, right? So these blue circles, right, stay blue circles. And that's the idea of the trivial representation. If we choose as a representation row instead the standard representation of SO2, right, that basically give us 2x2 rotation matrices, we can now look at vector fields. So for each pixel, right, now we associate a two-dimensional vector. And when we rotate a vector field, we are not only moving, the pixels into the new positions, but we are also rotating these two-dimensional vectors attached to each pixel. So that's kind of what happens in this bean here. So each single vector V is rotated by G. Yeah, makes sense. Now, okay. So finally, we can go into details on how we build a steerable CNN. So we have to import a few things from the library. So we already imported group before to play with all the group and group representation related objects. G-spaces is basically a sub-package that models essentially the full group that we use, because we don't want to be equivalent only to rotations. We are usually equivalent to rotations, right, G, and some translation Rn. So G space is the space Rn with the action of G on top of it. So for example, it would be En, if you want to give it a more precise name. And N is like in PyTorch, this contains the neural network modules. So the first step to define a neural network is defining what G space we care about, because it's not sufficient to say the group G. We also need to define how the group G acts on our pixels. So in this case, we define the G space of the 4 rotations, so the cyclic group of order 4 acting on the plane. And yeah, you see that this has a name, C4 acting on R2. Fiber group returns you the group G that we used. So C4, the group C4 of 4 rotations. Don't worry too much about the word fiber group. It has some mathematical interpretation, but for us, it doesn't matter so much. It's just a shortcut to get C4 out, because we needed to build some representations later. Then with respect to a normal PyTorch neural network, instead of working with the tensors, we work with basically some geometric tensors. Geometric tensors are just essentially PyTorch tensor, which carry some kind of type. To draw some analogy with programming, rather than having like variables without types, which is kind of like the PyTorch way, we have basically tensors which carry some type, which defines how these tensors should transform. So in connecting to what we said before, a tensor is just a vector in some vector space, but it does not know anything about how the group acts on this vector space. A geometric tensor instead carries some type, which is just basically a way to tell how the group we care about acts on this vector space. So before building tensors, we have to define what types are. So a field type, right, basically combines a choice of representation row that tells us how the channels of a vector field transform, and a G space, which tells us basically how the group transforms the base space. And if we scroll back 1 second to the definition, right, of these feature fields, what is it? Yeah, here you see that basically a feature field F need to know precisely these two objects: the representation row that transforms the channels, and the way the group G acts on the pixels. So all of this is encoded inside, inside a field type. So to instantiate a field type, we choose a G space and a representation of the fiber group. Okay, and for example, we pick the regular representation of the cyclic group of order 4. We're gonna basically build a group convolutional neural network as a first example. Now, like in a normal neural network, you usually want to have a lot of channels and go very wide, because the wider neural networks are more expressive and more powerful and so on. So to do that, it doesn't make sense always to build like a really big representations. What makes more sense is to choose one convenient representation, right, like the regular one, and then repeat it n times to basically build very wide feature fields. And to do that, we just use essentially the direct sum, which we have already seen earlier. So to draw some analogy with a group convolution, in a group convolutional neural network, you would basically pick regular representation to model the number of rotations, and then the number of copies of it would kind of corresponds to the number of individual channels that you have in a normal group convolution. Next step are what kind of features we use for the input. Well, typically, the input of your neural network is kind of defined by the task and the dataset you're using. So you generally know a priori what is the transformation type of the input. And if we work with images, as we said before, we have just the trivial representation that just tells us that the colors of a grayscale image don't change when we rotate the image. But sometimes you may have some vector fields in input, like I don't know, if you have some force field or wind field by some that you find in some weather data, right? In that case, you can pick as a representation for the input the standard representation. Or in the example that Eric said, right? Sometimes you have both, right? You have some data that is a wind field. You have also some heat map representing, I don't know, the temperature on the map, right? So your input should contain both a vector field and a scalar field, and you can of course combine them. But yeah, so that's how we define how our inputs should transform. Okay, so now we basically have defined how the input of the neural network transform. We said that in the intermediate layers, we want to use the regular representations, like in a group convolution. The answer I've not given yet in this hour and a half tutorial was how do we build equivalent layers, which seems like quite an important question to ask. Unfortunately, there's no time to really go deep on this, right? But that's pretty much the purpose of the library, because like so far we just use the library to give names to things, right? To annotate features, to annotate tensors. But the main power of the library is essentially solving this constraint. Once you use everything that you had so far to basically define how the input of your layer should transform, how the output of each layer should transform, you can just rely on the library instantiating the neural network modules that guarantee these modules are satisfying these equivalence properties. That is, when the input of your neural network transformed with some input representation, then it's guaranteed that the output transforms accordingly. For more details on this, I don't know how deep it goes in the lecture.
Maybe I can comment on. So in the lecture, I went to the path by, okay, let's just pick convolution kernels that are expanded in a steerable basis, like these circular harmonics. And then if you convolve with these basis functions, you get something on which your rotation representation acts, right? So you have actually steerable, you have feature fields with fibers that can be rotated in some sense. And so you can also imagine if you convolve with an isotropic convolution kernel, like which has a rotational symmetry, you create something which does not carry any directional information in it, because if I rotate the kernel, it's still the same output. So that was like a bottom-up construction that pick this steerable basis function, and what comes out are these fiber fields. Now the other way around is like what Gabriele is presenting is, and implement this now. If we want to have an output field which transforms in a particular way, well, then the code figures out, okay, what kind of basis function should I pick such that it satisfies.
Yeah, exactly. And that goes a bit more technical how that is solved. So I don't think it's really worth going too much in detail. And that's if you're curious about it, right, you can find some references at the end of the tutorial, but that gets a bit more complicated. So that's why it's nice to use some code that solves the problem for you. But the intuition behind it is quite similar to pretty much what Erika has shown in the tutorial, in the lectures, and and it essentially boils down to finding the right basis functions to use. So okay, that's the basic construction. This is the equivalence constraint we want to solve in practice for convolutional layers. Let me skip over this. Here you can prove that basically this equivalence constraint actually guarantees equivariance, but you can try that yourself. And now we can go a bit more in the neural network part. Okay, this is how you instantiate a convolution layer. So like you would do like from pytorch.nl import conv2d, right? Here you import R2 conv, just to say that it's a convolution over R2. And rather than specifying the input channels and output channels, this time you specify the input type and output type, which is essentially kind of telling you the number of channels plus how those channels are supposed to transform. We can try to generate some random input. If you take a torch tensor and you wrap it with a input type, it's going to return you a geometric tensor, which is nothing more than just a torch tensor associated with a type. So it's just like a typed tensor, and that's just used for the library to internally check that everything is equivalent. Because if you feed an input transforming according to the wrong representation in a layer that expects a different representation to be equivariant, of course everything is not working anymore. So this is mostly useful for automatic type checking. And we can now check equivariance. You can run this code yourself, and you will see that essentially what we do is for each group element, we take the input x, which is a geometric tensor, conveniently it has a function dot transform of g that transform the input. You can feed the transformed version in the convolution and check that basically the result is equal to transforming the output y when you transform just the output. So yeah, that's pretty much a couple of checks you can do on equivariance. Let me move a bit faster. You have other operations like ReLU, right? ReLU can only be applied whenever you have a regular representation. You can try yourself to see that if you apply ReLU on a vector field, that is kind of breaking equivariance, because it's kind of masking out part of the plane where a vector could rotate. So it's important to use only regular representations when you have ReLU. But apart from that, you can check that this is equivalent as well. And let's go, okay, something else important here. You can use the equivalent of a sequential module in PyTorch to basically stack multiple equivalent layers in a deeper equivalent neural network. This is going to check automatically that each consecutive layer is compatible with the previous one. So the input type of the second layer must be equal to the output type of the first for equivalence to actually work out. And you can check that overall the deeper network is still equivariant. There exists some pooling layers. This is essentially similar to average pooling in PyTorch, with some with some anti-aliasing trick to basically avoid some aliasing issues due to discretization sometimes. But yeah, and then finally we have some group pooling, which is used to basically take the equivariant features at the end of the neural network and turn them into invariant features if you want to do some kind of a invariant classification, for example. Okay, the last step is like how to build like an equivariant neural network with an infinite group G. What we did so far was using the group of discrete rotations, such that the result was kind of similar to a normal group convolution. So it's not so interesting, right? That's kind of the same you would get if you build a group convolution yourself with a discrete group. Of course, this is interesting when we take continuous rotations. So we can build the right G space by picking n equals to -1. That's just a shortcut to say infinite rotations. So you see, this is actually the group of SO2 acting on R2. The fiber group is SO2. We can build feature types like before, essentially the same strategy. But this time we build, instead of the regular representation, we build this band limited regular representation only up to certain frequency, for example, 2. And with respect to before, we cannot apply ReLU anymore because ReLU is equivalent only when it's applied on the function, right, sampled on each group element, which we cannot really do explicitly. So what we do here is instead of relying on some kind of approximation of ReLU by taking our features, which are stored in the Fourier domain, we take an inverse Fourier transform by sampling this function on a very large number of samples. Then we basically take the nonlinearity in this ReLU or ALU, right, in this on these discrete samples, and then we apply some approximate approximate Fourier transform to recover again the Fourier coefficients. The trick here is that if we make sure that the input is band limited and the number of samples is sufficiently large, we can guarantee that this kind of approximation is actually still equivariant and the error introduced is not too large. Yeah, this would maybe require a few more words, but like you can just use this as a module where you basically specify the number of channels. You can use this to build your regular representations, essentially. The maximum frequency is specified by this method. The number of samples you want to use to discretize the group when you take the nonlinearity. And then you can basically, you can take the input type and output type of these modules to use to build later layers. So now you can build your convolution, which maps to this feature, the input features to these hidden features, and these hidden features were actually the input of the nonlinearity. So the nonlinearity takes care of building the right representation that would make all this computation work out. So you don't have to worry about building the right regular representation. And then you stack again batch norm, your nonlinearity. You can use another convolution, which uses this new intermediate representation, and so on, like a normal convolution network. We can check the equivariance of this. And if you now check the equivariance, quite sadly, it turns out it's not equivariant. And so I usually ask this as a question for you to look at the answer, to answer. There's not too much time, but I want to at least try to see if someone wants to attempt to answer this question. Why do you think that a convolutional neural network to SO2 with this construction is not passing this assert? Yeah, someone wants to. Yeah. Yeah, so that's exactly one point. So that's the first point. This Fourier nonlinearity is essentially discretizing the group. It's taking a lot of care on discretizing it properly such that the error is minimized, but there is always some amount of error, which you can minimize by increasing the number of samples, but that comes at a cost, right? So there's a trade-off happening there. The second reason is also, well, that's a good reason. There's a second reason, and it's the fact that an image is actually stored on a pixel grid, which is not really symmetric to continuous rotations. You cannot really rotate an image without doing an interpolation, unless you rotate only by 90 degrees. And that is also happening when you actually use the filters of your neural network are going to essentially build some kind of rotated versions of a number of filters, which introduce a level of some interpolation artifacts, right? So overall, the neural network will never be able to be perfectly equivalent to continuous rotations whenever you work with data that is on a discrete grid. That being said, right, so it's hard to really pass this kind of test, right? But I want to, in the last few minutes, run here. We can still compare an SO2 equivalent network with a normal CNN, right? Trained or also randomly initialized on discrete data, and you can check the equivalence error. So the kind of the amount of the difference between the output of the input and the output of the rotated input, right, in relative terms. And you can see that even if the SO2 equivalent one is not zero, right, so the error is not zero for every rotation, that would be perfect equivariance, is still much lower than a normal CNN. So like a normal CNN like is equivalent only to 0 rotations by an angle 0, right? But then as soon as you rotate by a bit more, right, the error is very high, while an SO2 steerable network manages to control a lot this error. You can see nicely that there is a pattern where this is periodic by 90 degrees, because that's actually guaranteed to be perfect. So the error at multiples of 90 degrees is 0, and everything in between is kind of controlled and does not explode. I'll jump very quickly to the experiments here. We just download MNIST. We build an SO2 equivalent network, which is a bit deeper. We train it on MNIST. We also do the same. Okay, this is the SO2 equivalent network. You can see the accuracy for every rotated version of the test set, which is kind of varying, right? But it's still quite similar. Like the accuracy ranges from 95.2 to 95.5, which is not that large. To put this in relative terms, we can build a C4 equivalent network, right? So this is essentially the group convolution you did last week, right? We can do the same process, train it as well, and we can compare the final accuracies. And you see that the SO2 equivalent network is performing slightly better, but it's also more stable, right? So the C4 equivalent network is also perfectly equivalent to these 90 degrees rotations, but the variance within this in the accuracy, right, between these in all the angles between 0 and 90, right, is much larger than the SO2 equivalent one. And usually, like, the trade-off is not, of course, having perfect SO2 equivalence, because that comes with some additional cost in increasing the number of samples. But what this structure provides you is like a way to find the right balance in between. Yeah. But like you should imagine that the equivalence is not only at 90 degrees rotation, right? It's just a chance that the best performance of the C4 network is at this specific type of image, right? And then you just have a periodicity of 90 degrees. But the fact that it has a lower performance on 0 is kind of relative, right? Because like digits appear in every rotation, right? And the neural network kind of learns a random kind of phase, I don't know, a random basic orientation. So no, the dataset is trained on augmented digits. Yeah, so there's not really a bias on 0. The only bias that is there a bit is that to also generate the augmented dataset, right, you do rotate digits, which introduce some interpolation. So there is a slightly bias towards digits which are not rotated because they do not include an interpolation artifact. So there's a bit that, right? But yeah, thanks for the question. Yeah, that concludes the tutorial. Sorry for rushing. I did the last part. You can find some more reference at the end and some more comments, but I would encourage you to try building this, answering these questions and trying to build these networks on your own. You can find also like on Colab the unfilled tutorial to try yourself. Yeah, any other questions for the last few minutes? Okay, then thanks.